We have triangle ABC, its circumcircle. Points B0 and C0 are the midpoints of AC and AB, D is the foot of altitude from A, G is the centroid, and we let X be the point such that the circle B0, C0, X is tangent to the circumcircle of ABC. And so we want to prove that the points D, G, X are collinear, which is the same as saying that X lies on this line, the line GD. And we first notice something interesting, which is that this point GD actually passes through quite some interesting points. One specifically is the top point I have drawn up there, which I'll call A prime. It is a reflection of A across a perpendicular bisector of BC, and the second point is the altitude from 0 to B0, C0. And so we will prove that both of these 2 points actually lie on these the line DG. Actually, we only need to prove one of them, but we are going to prove them both here because there are two solutions I want to share with you today. One makes use of the first point, A prime, and the second makes use of the second point, which I'm going to call point Q. Okay, so firstly, let's prove that A prime lies on DG. And to do this, here's a pro tip. Whenever we deal with the centroid G, we always want to think about some sort of a homothenity centered at G, specifically one of ratio -2 or -1/2. For example, we can connect this and we can call this point A0, which is the midpoint of BC. And as we all know, BG to GB0 is 2 to 1. CG to GC0 is also 2 to 1. That is a property of the centroid, which is that all the medians are cut in a ratio of 2 to 1 by the centroid. And so if we perform a homothenity at G with scale factor or ratio of -2, then we will map C0 to C, B0 to B, A0 to A. And so we will map this entire triangle to this triangle. So this is a similarity that is occurring under a homothenity. And so everything that we take that are similar in these two triangles, it will also be a homothenity here. They will also be transformed under the homothenity. Let's take a look at point D here. So how does D relate to the triangle A0, B0, C0? Well, D is on this circle, and the reason being is that we know that C0 and B0 is halfway in between A and BC. And so D, since D lies on BC, and this is all perpendicular, we have that D is actually just a reflection of A down here. And A0 is rotating A all the way down here, or passing through this middle point, and also sort of a reflection, but we can also call that a homothenity at G. And so what's happening is that D and A0 are actually reflections of each other across the perpendicular bisector of B0, C0, since one is A0 transformed over here, and the other one is A transformed down here perpendicularly. And so when we map D under this homothenity, it will map to the point A prime, which is a reflection of A across perpendicular bisector of BC, just like how D is a reflection of A0 across the perpendicular bisector of B0 and C0. So D will map to A prime, and that means that DG has to be collinear with A prime, or that these have to be the same line, specifically with a ratio of 1 to 2, but we don't really care about that much about that in this figure. So we have proved that DG and A prime are indeed collinear. So now that I think about it, let's actually go with this first solution first. Let me demonstrate this first solution before we move on to the second one with Q. And so instead, we want to prove that X lies on this line DG A prime. And what we can do first of all is the method of false positioning, which is to first assume that, let's say, XD passes through or intersects the circle at another point, let's say T. Well, we don't really care about G anymore. We can just use D. And so essentially what we want to prove is that angle DAT is equal to 90 degrees. Because if we prove this, then T is just a reflection of A, or T is just A prime, which is what we wanted. And so we have to chase this angle down a bit, but we still haven't used the fact that x, or these two circles, are tangent to each other at x. And so how can we actually use that piece of information or condition we are given? First of all, we can draw the circle AC0, B0. By the way, it also passes through O, but it's not of our concern here. If we draw this circle, we know that this circle is tangent to the circumcircle at A2 because we can perform a homothety at A with scale factor 2, and that will map C0 to B, B0 to C, and this circle to this circle, so these two are indeed tangent at A. And what we can do is we can use the radical lemma on these three circles, which is that their pairwise radical axes are concurrent. So the tangent at A, B0, C0, and the tangent at X, these three lines are concurrent. And so we can actually come down here because I've drawn them here. If we draw these three lines, they're concurrent at a point, let's call it W. And let me draw back my XD and T. Okay, so what's cool is that W is essentially the common tangent, or W is the point such that WA is tangent to the circumcircle and WX is also tangent to the circumcircle. But from the fact that X is tangent, or that these two circles are tangent at X, we also know that W lies on B0, C0. And what's interesting is that we've previously stated that A and D are reflections of each other across B0, C0. So essentially they're symmetric about B0, C0. So if we draw the line WD, then WD should be equal to WA, which is equal to WX. And so that actually fully utilizes the information that W lies on B0, C0, and hence fully utilizes the information of X. The reason being, if W didn't lie on this, then obviously these 2 points will not be equal. Because, well, C0, B0 is the perpendicular bisector of AD in the sense. So, with the point W, we've actually fully realized the conditions of X, the conditions we are given of X. And since we know that WA equals WX equals WD, it is very natural for us now to try to draw a circle around AD and X, and it's centered at W. And well, that's a bit, it's like covering everything, but let me try my best. One stroke. Okay, this passes through X. Trust. And how can we use this information now? Well, we'll use this information in a moment, but we also know that WA is a tangent, so this is right angle, and this is also right angle. So we know that WA, O, and X are actually also concyclic, with WO being the diameter of the circle, but that's not really of our concern here, but let's just mark it down that they're concyclic. So we have 4 circles now. The circumcircle of ABC, C0, B0, X, the circle center at W, passing through ADX, and we also have WAOX. We have a total of 4 circles, and what we want to prove is that DAT is 90 degrees. So this is kind of like the ideal thing that we want in a lot of problems, which is we simplify the condition down to an angle chase, which means we want to find what an angle is. And we also have a lot of circles. Circles pair very, very, very well with angles. So this, I'll repeat once more because it's so important. This is the ideal condition that we want, to have an angle chase and also many circles. And I'll demonstrate how we can do this angle chasing here. For example, angle DAT is equal to, we can say, angle ADX minus angle ATX. And we know that angle ADX is actually just equal to half of 360 degrees minus angle WAX. And angle WAX, by the way, this is on the circle with center W, so we can actually use the center of circle condition. And then angle WAX, sorry, this should be AWX. And since we know that AWX and O are concyclic, we know that angle AWX is just 180 degrees minus angle AOX. And if we simplify this a bit, this is 90 degrees plus angle, or plus 1/2 of angle AOX. And then let's look at angle ATX. Well, angle ATX is just half of angle AOX by the circumcircle of ABC. So we know that this is angle half of angle AOX, which we eventually want to subtract. So if we subtract these two, we get that this is 90 degrees. Indeed, DAT is 90 degrees, as we desired. Okay, and then I will prove the second point, or show the second solution here. Actually, what I'll do is I will just copy this diagram down here. If you remember what I previously mentioned, I claimed that this point, Q, is actually the perpendicular from C0, B0. And so, again, as I've given the pro tip to you, is when we think of centroids, we think of a homothency with scale factor -2 or -1/2. They're the same thing. So, to prove that Q lies on the line DG, we just do another homothency. And this time we want to map D to Q. If we know that D maps to Q, then we will have shown the collinearity. And so again, I draw this A0 and this triangle, but this time, instead of considering D as part of the triangle A0, B0, C0, I can consider D as part of the triangle ABC. And now we map with a scale factor of -1/2, which means we map C to C0, B to B0, A to A0, and this entire triangle get maps to here. And then where does D get mapped to? Well, D gets mapped to this foot of perpendicular, or the altitude from, or the foot of the perpendicular, or the altitude from A0 to B0, C0. So why is that Q? Because we know that OA0 is perpendicular, since A0 is the midpoint, and we know that BC is parallel to C0, B0. And so since this is also perpendicular, they are collinear, and Q indeed is the image of D under this homothency. Therefore, Q, D, and G are also collinear. And we want to prove that X also lies on this line. And how do we do that? Well, first of all, we have to spot some more circles like we did. Again, the essence is we want to get to an angle chase in the end. And we also want many circles, as many as we want. There's no harm in more circles. So let's take a look at what's concyclic here. Again, we can look at the circle WAOX, and this time we actually have a new addition, which is the point Q, because we know that OW is a diameter and OQW is a right angle, so we know that these 5 points indeed lie on a circle. Let me just write that down first. WAQOX. And as before, we also have the circle centered at W with ADX lying on it, so let's just call it ADX, and I'm just going to add a centered W. Now, to prove that these 3 points are collinear, let's first take a look at what this line is. So we have QA, and since D is a reflection of A across B0, C0, QD is actually a reflection of the line QA across this. So essentially, if we can prove that angle AQW is equal to angle XQW, then we know that X also lies on this line because DQW is equal to AQW. So how do we prove this? Well, since we have so many circles, again, we just do some angle tracing. Specifically, this circle is really helpful here. We have that AQW is actually equal to AXW. Let me write that down here. AXW, which is equal, since WX equals WA, we have this isosceles triangle, and AXW is just equal to XAW, and by the same circle, we have that this is actually equal to angle XQW. exactly what we wanted to show here. So this time we actually didn't even use a circle. Well, we kind of just did use the condition that WA equals WD, but we didn't even use the circle. We still use the condition of D because we noted that AQW, angle AQW, is equal to angle DQW. That is what helped us to show that these 3 points are indeed collinear. Alright, so those are the two solutions, and I felt that this problem was really rich in takeaways, especially for me because I somehow didn't come up with this idea. Like, I noticed that there was this point W, which is the concurrent point of these three lines, but I didn't really think about the circle centered at W or the circle WAOX or anything. And I guess the takeaway from this problem, well, there's multiple takeaways, but first of all, we had to utilize the condition of X, and after we spotted this radical lemma thing and found the point W, it's actually really helpful because we can transfer all the information from X to W, and that is very reliable. We also have that WA equals WX equals WD because of this reflection here, and then we found the circle. So the first key takeaway here is, this is the fourth time I'm repeating it, but I will do it again because it is so important, is that it is optimal if we can transform our problem into some sort of angle chasing condition that we want to show. And then we just get many circles and angle chasing becomes really easy. And one thing to note is also that centers of circles are pretty helpful too, because for example, if we have an angle over there, we know that this is double of that angle, so it also helps a lot with angle chasing. And the second thing is to be more aware of these transformations. For example, we use a lot of transformations in this problem, the homotopy at G, which maps C to C0, B to B0, A to A0, and we see where the points get respectively mapped to. And then we also have the reflection across B0, C0, which maps A to D. That is exactly how we knew that WA equals WD and how we passed this information on there.